Standard Model will be part of it. Mind you, this image isn't the Standard Model itself, but it represents all of the important components. For instance, we see here in the upper left-hand corner 6 particles called quarks. As you can see, some of the quarks are found inside protons and neutrons in the center of atoms. At the bottom left, we have 6 particles called leptons. Leptons are the lightest of the subatomic particles, and the most familiar one is the electron that is found in the outskirts of every atom. Over here on the right-hand side, we see there are 4 particles that are simply called force-carrying particles, or sometimes, for technical reasons, called gauge bosons. They are responsible for transmitting 3 of the 4 known forces. And here in the center, you see the ghostly field called the Higgs field, and a particle called the Higgs boson, whose existence was confirmed only in 2012 and was the final missing piece of the Standard Model. In the next several lectures, we're going to talk in detail about each piece of this chart so you can understand what you're seeing. The overview will help you understand how the things fit together. So let's start by talking about the known forces. We know of 5, or maybe it's 4, or maybe it's 3. The complication arises from the fact that we're living through a period of unification. Over the last 2 decades, we've unified forces that historically have seemed distinct. That's incredibly exciting, but it also leads to a bit of confusion. So let me clear that up a bit. I'll start by talking about the 5 forces and show how they can be thought of as 4, and maybe even 3. The 5 known forces are gravity, which keeps us firmly planted on the ground and guides the planets through the heavens; electromagnetism, which covers both electricity and magnetism, of course, but also light and chemistry; the strong nuclear force, which binds protons and neutrons together in the nucleus of atoms; the weak force, which is responsible for some forms of radioactivity; and finally, the Higgs field, which gives mass to subatomic particles. Those are the 5: gravity, electromagnetism, the strong force, the weak force, and the Higgs field. So how do we get down to 4, or maybe even 3 forces? Well, in the late 1960s, physicists showed that the weak force and electromagnetism were really 2 facets of a single thing, much in the same way that electricity and magnetism turned out to be 2 facets of something that we now call electromagnetism. Men and women are 2 facets of a single thing we call human. You get the idea. Therefore, scientists often talk about an electroweak theory. So we might say that the forces are gravity, the electroweak force, the strong force, and the Higgs field. On the other hand, the Higgs field is inextricably tied with the electroweak force, so maybe it can get tucked under the electroweak umbrella. Under that way of thinking, we have about 3: gravity, the strong force, and the electroweak complex. Let's talk a bit about the forces. We should be careful, since the word force has a familiar meaning. It could mean something like pushing a car out of a ditch, or even, these aren't the droids you're looking for. The better word is interaction, because the word interaction means that some change is caused, like changing a particle's identity without actually moving it. However, the word force is ingrained in the literature, so we'll stick with that word most of the time. Strong force is the strongest of the known forces. For example, it's the force that explains why the sun burns so very hot. So the name is apt, it really is strong. But it also has a weird behavior. It's incredibly strong over very short ranges, say the size of a proton. Once 2 particles are separated by a distance much larger than that, the strong force goes to 0. It's a little like Velcro. If 2 pieces of Velcro are touching, they're strongly bound together. But once they're separated, they feel no attractive force at all. That particular facet plays a big role in understanding the large range observed in the mass of atoms. That's the strong force. The next strongest force is electromagnetism, which unifies electricity and magnetism into a single force. It's much weaker than the strong force, but it has a different behavior as far as distance is concerned. 2 particles experiencing the electromagnetic force will, in principle, feel a force between one another if they are located on the opposite sides of the universe. Granted, that force will be very small, but it won't be mathematically 0, because electromagnetism has an infinite range. Because of the difference in how the 2 forces change with distance, you have to be very careful to specify distances when you compare electromagnetism to the strong force. So we traditionally pick a separation distance of about the size of a proton, which is a femtometer, or 10 to the minus 15th meters. At that separation distance, the strong force is about 100 times stronger than electromagnetism. Of course, given the short range of the strong force and the infinite range of electromagnetism, if two particles are separated by just a meter or even a millimeter, electromagnetism is actually much stronger. The next weakest force is the weak force. The natural range of the weak force is about 1/1000 the size of a proton. However, if we ask how strong it is at the separation of a femtometer, it's about